Welcome to our next lunch talk. I'm very glad that we have a team from University of Geneva speaking today about deep geothermal energy and its impact that it can make for reaching our climate goals. So Luca Guglielmetti, Yasin, and Andrea Moscariello. I think you will all speak during this talk, so you will get to know them. I would like to give the floor now to Luca, who will start. So Luca, please.
Yes, good morning everybody. Buon appetito, guten appetit. With this presentation, it's something that we prepared. Yasin, my colleague, Andrea Moscariello, who is the leader of the research group we are all working, and myself. The goal of this presentation is mainly to introduce you a little bit on geothermal energy, how it fits into the Swiss energy strategy and energy system, and we will provide two examples on how we can eventually integrate all sorts of data that are available and that can be collected to evaluate the potential of geothermal energy, in particular deep geothermal energy and storage in Switzerland. We all know that we have to decarbonize our energy system. These are global statistics from IRENA, and we see that at the global scale, we are still very much dependent on fossil fuels. And Switzerland is not much different in terms of shares. If you look at the power generation from renewable energy sources, we see that very much is still dominated by hydropower. And if you look very closely to this slide, you see at the top of the column a little red bar which represents geothermal energy, which zoomed in shows that there is a trend for sure of increasing in installed capacity and power generation from geothermal. This is mostly linked to countries which have very peculiar geologic condition. And this growth at the global scale also is mostly dominated by emerging countries like Turkey, that in few years installed more than 1 gigawatt of installed capacity. Geothermal can provide for sure benefits because it is a renewable energy sources, it is sustainable. It can provide base load energy with very low carbon footprint. Life cycle assessment analyses have been performed, for example, in Europe, funded by the European Community, and they demonstrated that geothermal has a very low carbon intensity compared to other, not only renewable energy sources, but in general. And we know, we have seen from the plot before that half of our energy consumptions is still needed for heating and cooling applications. And geothermal can play a big role in this sector. We see that geothermal can provide quite a broad range of solutions for the heating and cooling sector, which about 30% to supply district heating network. Balneological uses are very much developed. Spas and also greenhouse heating is one of the main applications. With globally, China being the leader of the heating and cooling application. And if you look at Europe, Germany for sure, and France are two major countries leading the heating and cooling sector, also the Netherlands. Switzerland has a base load of shallow application, ground source heat pump, very much developed. In terms of deep geothermal, we will see later the journey as being a little bit tricky. But what is geothermal energy? Basically, geothermal energy is the heat that is naturally stored in the subsurface that can be extracted by drilling deep wells to supply energy for human activities. When usually I teach to students, I always show this slide because this is a little bit of what the general public think that geothermal energy is. You know, there's lots of hydrothermal features, volcanoes, geysers, fumaroles, but actually geothermal is a resource that is invisible. And this is because heat is available everywhere. The point that complexify the geothermal energy production is to find the suitable site where we can extract such heat. And this is quite complex because when we are dealing with subsurface conditions that determine different type of potential target in the subsurface. You see in these two sketches which were published by the Bureau, the French Bureau of Geology, that there are different type of geothermal system, and or we can call them geothermal plays, which actually are associated to different type of subsurface conditions. On the left-hand panel, you can see that there is a context that is much more familiar to Switzerland, which is the sedimentary basin, which is the geologic context very similar to what we have in the Swiss plateau, where we have different target. The temperature increases with depth, about 30 degrees per kilometer. Therefore, it is relatively easy to characterize the temperature distribution in the subsurface. The deeper we go, the hotter we get. And we can reach temperature of about 100 degrees at 3 kilometers in depth and 150 at about 5 kilometers in depth, which are the main target for deep geothermal. There are also systems where we know that there is quite a lot of heat that could be potentially extracted, but the rock is not fractured, it's not permeable. Therefore, we need to stimulate this rock to inject water and then extract it furthermore. And these are the classic example that we had here in Switzerland was the case in Basel, where was not totally successful because due to the injection operation that they performed, they had problems with induced seismicity. Another type of geothermal play is what we call the magmatic system, and these are typical of, for example, Iceland or Italy, if we think about Europe, Turkey, where they have very high temperature and the fluid is mostly vapor or vapor dominated, therefore with higher enthalpy and higher potential for power production. To create a geothermal resources, the ingredients are basically three, but the combination of them is quite tricky to achieve. The first we saw it's heat, which is naturally stored in the subsurface everywhere. Then we need a fluid that acts as a carrier that extracts the heat from the subsurface, and then we need permeability. Permeability is the property that allows the fluid to flow, and we can have fluid in the liquid phase, as for example, we have in Geneva or everywhere in Switzerland, and the left-hand side picture clearly shows a geothermal well in Geneva with quite high flow rate, and then we have steam phase, which is typical of the high enthalpy fields. You see this well, which is from Italy, that discharge dry steam at 180 degrees. But permeability is the tricky part, because you can see these two examples from Geneva. On the left-hand side, you have one productive well. You see this quite impressive sort of geyser at the Geo01 well, 750 meters, 34 degrees, 50 liters per second. The same reservoir was drilled on the southern part of the canton of Geneva, and the result, you can see them on the right-hand side movie, which are very poor. If we manage to combine these three ingredients, the application of geothermal energy are very broad. They can go from power production at a higher temperature to a broad variety for low temperature resources. And this is actually the one between, let's say, 5 to 100 degrees, 120 degrees are the ones that are the most interesting for Switzerland. If we go back a little bit to some statistics, Switzerland is for sure Still, the energy system is dominated by fossil fuels. The renewable energy play a relatively small role, in particular for the heating and cooling sector, whereas power is mostly generated by nuclear and hydro. If you look at the deep geothermal projects that have been explored or that are under development now, you can see that there are quite a lot of homogeneous distribution if we look at deep geothermal, but if we specifically look at hydrothermal projects, the story is a little bit different. You see very few greens and quite a lot of yellow, orange, or red, which represents the site that are in development or have been abandoned. And with this slide is just to give you a picture of the journey of the deep geothermal project in Switzerland, where only very few projects were successful at the moment, but a lot is going on now because the Swiss Federal Office of Energy and the Confederation implemented some support measurements to reduce the subsurface, the geologic and the financial risk of the prospection and exploration phases, which rely on all the activity that as geoscientists we do to understand what's down there. And to encourage this development, the Swiss Federal Office of Energy funds up to 30 million per year, if I'm not mistaken, project aiming at deep geothermal resources. But if we look at how geothermal can supply energy for heating and cooling, we have to look at the subsurface for sure, but we also need to look at the surface boundary condition. In particular, in this map, we see the distribution of the heat demand, that it's a criteria that is very important because it's spatially distributed all over Switzerland as the subsurface resources. They are very heterogeneous spatially, horizontally and vertically. And then we need to understand how we can distribute and eventually connect the geothermal resource to the supply system, the district heating network. In terms of subsurface, we saw before that there are different plays, different potential targets. In particular, if you look, for example, at the heat flux, two main regions, the Canton Aargau, the northern part of Switzerland, and the central southern part of Switzerland might have some very encouraging temperature distribution. However, as we said before, having just temperature is not enough. We need faults, for example, to increase the permeability. We are lucky enough in Switzerland to have a very detailed subsurface 3D model that allows screening in a first instance where can be the resources. And you can see that there is a superposition of different potential targets in different aquifers. So how can we combine everything? And this we will go a little bit more in detail on what we are doing at the University of Geneva, is actually that we need to combine supply and demand. And this can be achieved by performing spatial multi-criteria play-based analysis studies, which allow evaluating not only how much heat we can extract from a subsurface, but where and for which demand. And now I give the floor to my colleague Yasin, who will explain a little bit better how to implement this type of approaches.
Thank you, Luca. Hello, everyone. I'm Yasin Makhloufi. I'm one of the colleagues of Luca. We've been working together for quite a long time now. We started on the same day, actually, back in 2016. We worked on several projects, and a few years ago came along a problem, which was how can we manage all of these data? As Luca showed you, in order to better characterize this geothermal system, there is a lot of data that you need to compile, and you need to have access to both in the subsurface and in the surface. So what we did at the University of Geneva is create and maintain one of the most up-to-date databases containing both surface and subsurface data all along the Swiss Molasse Plateau. To do that, we collected all of the data coming from literature, from Swiss Topo, NAGRA, some cantonal energy providers, and of course, all of the research projects that we led in the past years at the university. And the way that we found to do so was to use a GIS-based software in order to both manage and compile this database. We decided to focus on 5 main areas of collection. Of course, the Geneva area, where we led most of our project at the university, but then we moved on with several other projects, and we had the chance to collect data on what we call the Vaud area, the Fribourg and Bern area, the Northern Switzerland area, and the St. Gallen area. So as you can see, all along the Swiss plateau, we were able to collect this kind of all of this data from the surface and subsurface. So, something that is really important for us is the metadata. You know, this is the data associated. This is the data about the data. It's really important because it gives you a lot of information about when was the data acquired, who acquired the data, is it public or not. Swiss Topo, for example, you have an extract of metadata coming from Swiss Topo on the left side, and on the left side you see that we try to conserve all of the metadata, and sometimes we also add the metadata to this database when we know it, and you will see why it's really important to have this other source of information. At the core of our database is the wells. As you know, deep wells, what we call deep wells, is wells deeper than 500 meters, especially for, using the Swiss Topo referencement. This well gives us a lot of information about the subsurface condition, about the reservoir properties, about the different rock layers that you encounter in the subsurface. So this is one of the main core object of our database is this well database. We use the same structure as Swiss Topo in order to be compliant with them. And we update this database as soon as we can with all of the new wells that are implemented in the Swiss plateau. What we care about this database because we have 2 types of very important data. Here you see an example of one well. This is UniGe 2, which is a really important well for us in Geneva because this is the only well that crossed the whole stratigraphic section, all of the rocks in the subsurface, and when we have a core. So we have direct access to the rock samples of the subsurface. So the red part of the data is this typical data with the name of the well, the owner, the depth, the coordinates, the location of the well. What is really important for us is the bottom part of the data, which is in green. And here you can see all of the data that are available, such as the chemistry, the mineralogy, what are the reservoir properties, do we have any reports on the well, do we have all of the data acquired during the well operation. And also a really important state is what is the confidentiality of the data, are they available? Are they collected in the database, and are they public or private? So this is the way that the data is organized. Apart from the well, another really important data is the seismic data. Seismic acquisition is a tool used by geologists in order to image and better understand the subsurface. Here you have a few examples. You have 2D seismic lines, and as you can see, they gave us a clear image of what the subsurface looks like. It helps us in identifying different geological units in the subsurface, what is their depth, what is their configuration, but also are they crossed by structural faults. And these faults are really, really important for us. Luca, if you can go to the next slide. Yes, thanks. Here you have this map, which is the collection of all the 2D seismic lines. This is the black lines in the map. You see that the Swiss plateau was well explored in terms of seismic acquisition. Most of the acquisition was done by private company, and the data is not accessible. This is why I told you that it's really important for us to have access to this metadata, to know who owns the data and who we need to talk to have access to this data. And in the case of seismic data, especially the dark lines that you see here, the 2D seismic, some of the acquisition is quite old and need to be reprocessed or reinterpreted by us geologists in order to have this clear understanding on the subsurface. And then we have 3D seismic, which is another kind of seismic, which is really important because it gives us a 3D image of the subsurface. And we have some acquisition of this kind of 3D seismic in Switzerland, such as in the northern part, Saint-Gallen, and very recently in the canton of Geneva with the 3D seismic survey that was did last summer. And I was telling you about faults. Faults are these structural features in the subsurface where, due to tension, rock will break apart and you will have this fault line that you must probably have already seen in the paysage around you. We need to understand these faults because they can be very good source of fluid flow path inside our rock formation, meaning that we have the conduction of fluids, probably hot fluids, into the reservoir. So mapping and updating the structural data and faults is a very critical step towards understanding the subsurface possibility in terms of suitable reservoir for geothermal exploitation with this good flow properties. So this is an extensive work also of updating this structural database. And of course, like Luca told you, subsurface data are good and we are very interested in them because we are geologists, but surface data are also very important because there is an equation between the two when you look at geothermal projects. And in this database, we also try to collect all of the data concerning the surface. And here you have an example of this map, which presents the heat and cold demands, the different geothermal projects in this area, in the Zurich area, where are the incineration plants, which can have some residual heat that they produce, and maybe we can use for storage, and where is the location of the deep wells in this area. So with this kind of database, it's easy not only to extract data, add data, but also to visualize the data and perform some spatial data analysis directly in the database. If you are interested in this database further, we can organize something at the University of Geneva to have a live demonstration of this database. And also, if you think you can contribute or you are very interested, we can talk about this database. I give it back to you, Luca. Thanks.
Thank you, Yasin. So in the coming slide, we will go to some case study, in particular on two topics. The first will be aquifer thermal energy storage, which is a hot topic in the geothermal community, not only in Switzerland, but globally. Europe has just funded a 20 million project called Push It, where University of Geneva is part of it. And we will work for the next 4 years on evaluating how we can store excess heat in the subsurface. And then hydrothermal resources in Lenzburg. This is a joint project that was performed between the University of Geneva and the industry. So what is aquifer thermal energy storage? Basically, it can be a solution to recover excess heat discharged in the environment by industrial process, for example, during summer, store it in an aquifer, therefore in a volume of rock that allows storing this type of excess heat, and then recover it in winter, therefore contributing to supply it to the district heating network and eventually try to reduce the use of fossil fuels in this type of applications. Why we focus on the Swiss Molasse Basin? Basically because this is where lots of data are available. If you look, as we said before, there is this nice 3D model, geological model, which is perfect for this type of initial screening at the regional scale. And we also have the highest density, both of heat demand and excess heat. In order to implement the framework, we needed to conceptualize a little bit our understanding of the distribution of the heat demand and the potential target in the subsurface. Therefore, we identified two main potential targets in two geologic layers, characterized by their own specificities, by their own hydraulic properties and distribution of them. And we combine in this framework that you see here, the surface constraint, the surface criteria, which are mostly linked to the energy system, thermal networks, heat demand, and excess heat distribution. We also try to start to embed in this framework some economic criteria. For example, the levelized cost of heat. This was one that we performed. at the end, after combining the surface and the subsurface criteria. In particular, the subsurface criteria are quite complex. You need to integrate lots of source information and also embed the reliability of this surface, of this data. We saw from the slides from Yasin that we can get lots of data, geophysical data, borehole data, but they all have their own resolution. Not of these data were collected for geothermal purposes, therefore the results have to be evaluated carefully. In this type of study, we perform proximity analysis, assuming that the closer we are to the data source, the better, the more reliable they are. But as we enter into a more localized scale, we can perform much more advanced uncertainty evaluation using geostatistics, creating different type of models that can allow us to evaluate the uncertainty, for example, for fault structure or distribution of petrophysical properties. All this framework, which looks relatively complex, can be summarized by this equation, which is a weighted favorability assessment evaluation that allows to combine the different criteria, give them a weight, and therefore the sum of those will provide a favorability index, which is briefly shown here in these two maps. The left-hand side shows the favorability of storage in the upper reservoir, the yellow that you saw in the cartoon before, and the other one on the right-hand side shows only the favorable conditions in fault structure in the carbonates of the upper Mesozoic, because we assume that only faults are the suitable volume of rock able to host, but also recover the stored heat. Yasin?
All right, thanks, Luca. I will go quickly on a small project that was done in collaboration between Geneva Resources, which is a consultancy company based in Geneva, the University of Geneva, SWL, sorry, and HZ Argo. So basically, the municipality of Flensburg wanted to explore the possibility of a geothermal project in their municipality. And if you go to the next slide, Luca, please. So the problematic was there any potential for geothermal energy production in the municipality and the feasibility of such project? And the key solution that were proposed was to apply this kind of source to sink approach, meaning first characterize the subsurface geothermal potential, then identify the energy demand on the surface, integrate and analyze the different data that were available, geophysical, geological, fluid flow data, identify the different opportunities for geothermal project, and of course, assess the risk and the uncertainties of this project. The methodology that was used was basically first collect the data in the Lenzburg area, integrate and interpret this data, meaning integration of the existing data, identification of the data gaps, produce a revision of the old data, and the creation of new maps when necessary. And everything was put inside a database, a GIS database, very similarly to what is done at the university, in order to compose, analyze, and process the different maps. Once that was done, then was applied the spatial multi-criteria play-based analysis that Luca showed you earlier with this framework with the different inputs needed to produce the favorability maps. So some example of data integration and interpretation. On the left side, you see the heat flux map. And you see in this part, you have Lenzburg at the center of the map. And you see that the heat flux is quite high, reaching up to 110 to 130 milliwatts per square meters, which is almost the double of what is usually observed. On the center part, you see a new map that was created, which is the isotherm 120 degrees Celsius. And you see that in the Lenzburg area, which is in the middle, this isotherm is reached at about 3,000 meters depth. And another very important feature on the right, you see this tectonic faults map with the characterization of the new faults using seismic data in the area of Flensburg. So this is an example of the different integration and interpretation of new map needed in order to produce the favorability analysis. Another really important kind of data, on the next slide, please, Luca, is of course the reservoir data. Here you have an example of the porosity, the permeability, and the thermal conductivity of the different rock layers encountered in the subsurface of Flensburg. And also another important data is the chemical composition of the waters all around the district, which give you a very important information about the type of fluid and the different possible fluid migration path in the subsurface. Once you have all of this data, you can move on to create reliability maps. Of course, you want to understand what is the proximity of the data in your project, but also what is the quality of the data. This was done for all of the data collected. And if you see the example on the middle, you have the wells, you have the seismic line, you have the water sample, and you see the seismic line that cross the district of Flensburg. Obviously, the closer you are to the seismic line, the highest is the reliability of the data, and the further you go from the seismic line, the lower is the reliability. Combining all of these data, you have a global reliability maps, and you can do the same process of raster integration and raster computation in order to produce the favorability maps, where you have your faults, your permeability, your thermal conductivity, your temperature, and the different subsurface units, and you achieve a subsurface favorability when you see that close to the wells and close to the faults and close to the seismic data, you have a high favorability. And you can also directly identify where you have data gaps and where you need to acquire new data. Again, the adequation between what is happening in the subsurface and then the favorability achieved by mixing in the proximity with the surface conditions, such as the proximity to the district heating and cooling networks, and the spatial distribution of the heat demands, give you a final map with a favorability index, which indicates where are the different geothermal targets in function of the different geological units and what type of geothermal energy you could provide in this district.
Just to conclude the presentation, and then I will give the word to Andrea Moscariello to wrap up. This was another result of a Inno-Swiss project that was carried out between the University of Geneva, industrial partners, SIG and Geodesics and ETH. The idea was really to collect new data about the subsurface, but also to represent the result in an easy way that can be accessible to everybody, to understand where can be the most favorable area in the Geneva area before the 3D seismic. Therefore, everything now has changed for sure. But a web app is actually quite a nice tool that could be also developed maybe in the framework of SWIP. So Andrea, if you want to conclude, I give you the floor.
Yes, thanks a lot, Luca and Yasin. I think I have not much to add, except I would like really to highlight the importance of this work, which has been not done only on the context of the DeCarbCH. We have been working on this database since 2016 in a nationwide project, which is called UniGe, which was aimed and is still aiming at identifying the risk of finding hydrocarbons for deep geothermal exploration wells, following what happened in St. Gallen. So this has been a massive amount of work. Unfortunately, it's not an automated process, has been a manual work. And indeed, the database is as far as we know, the most complete as possible for relatively deep wells. But clearly, there is quite a lot of other wells which have not been put into the database. And clearly, that will increase our understanding of the subsurface, especially if we want to look at shallow or medium depth. I think it's very important to stress that this is an important effort that has to be done, has to be continued. In the context of the DeCarbCH project, we are focusing and contributing to the work package 1, where we try to identify potential for shallow heat sources for direct use and of course aquifer heat storage. But as Luca and Yasin clearly mentioned, geothermal is more than that. We do indeed have an effort of exploiting the deeper geothermal resources. We are very at the beginning of these adventures in the Swiss plateau, but definitely more will come, and hopefully successfully will come in the future. So I think that's it, and I'm happy to, and together with my colleagues, to answer any questions you might have.
Thanks a lot to the team from Geneva for this great overview.